Right. So we've got 5 more minutes, Nick.
Yeah.
Yeah.
We've got 11 attendees at the moment, so we're ready to,
Yes.
to start on time.
Ooh, and I need to keep the time. So can I check with the speakers? Would you would you like me to give you a warning at 14, like, say 1 minute more or something like that? Or I'll just go, the 15-minute alarm would go on my phone. Is that, how would you prefer that? Or
Two out of the 3 are pre-recorded videos, so I think just
okay, so
let them know if they're going on.
Yeah. So okay, so we have Moritz as a video, and then and Gherardo also has a video. Yeah. So people are still joining. We'll start at 7:15 on the dot.
So Mandy, did you want to give an introduction to the session, or shall I start that first video?
Hello, everyone. Welcome to this session of statistical modeling in R. So we've got 3 speakers today, 3 speakers lined up. So our first speaker is Moritz N, and he's from the Department of Statistics, Faculty of Economics and Statistics at the University of Innsbruck. And his research interests are computational statistics with applications in environmental sciences with graphical evaluation of probabilistic models. And today, he's going to talk about probability distribution forecasts. Please make him welcome.
with the title Probability Distribution Forecast, Learning with Random Forests and Graphical Assessment. My name is Moritz N and I'm currently a postdoc at the Statistical Department in Innsbruck. This is joint work with my colleagues Reto Stauffer, Lisa Schlosser and Achim Zeileis. In the next 15 minutes, I will firstly introduce the concept of distributional random forests. So essentially random forests, but the distributional emphasizes that we are not just interested in point forecast, but rather in full probability distributions for each single prediction. And secondly, I will show you how we can evaluate the goodness of fit for such probability models by our newly developed R package top models. So when we talk of regression, the starting point of all of this is of course the linear model or the generalized linear model, where the expectation, the mean of a variable I'm interested in, is modeled through a linear function of some covariance. In R we have of course the functions LM and GLM for that. If we want to extend that a bit, so allowing for smooth nonlinear effects in the covariates, we have the GAM. In R provided by the MGCV or VGAM packages, among a lot of others of course. And then over the last decade there was an increasing interest in so-called generalized additive models for location, scale and shape, or also called distributional regression, where I model not only a possible nonlinear change in the mean, but also in the variance, for example, or any other distribution parameter. Well, the package that started all that was of course the GAMLS package, but by now there are lots of other packages incorporating the same design as well. So all these models are additive modeling approaches, so classical parametric or semi-parametric models. When we move towards algorithmic modeling, the classic thing is of course the regression tree, where we recursively split the data into more homogeneous subgroups, fitting a piecewise constant model in the simplest case. And we have an example of such a regression tree here on the left. Here we have two cutoffs in blue, and depending on these cutoffs we land in three different terminal nodes in yellow, and we have the figure here on top. So we have here a lower, a higher and an intermediate expectation of the response values. Well, if we maybe not want to model such a step function but get a smoother version of that, what we could do is not model just one regression tree but several trees, maybe 500 trees on a subsample of the learning data, and afterwards we aggregate over these 500 trees. And that's what we call a random forest. So in R there's the package random forest of course, but also ranger and partikit. So the next step here is what we did in the classical additive setup before, not just modeling the mean, but to model the entire distribution. So similar to a GAMLS approach. And that's what we call distributional trees and forests. It's available in the package disttree, which is based on partikit. Well, to sum up here, for probabilistic forecasting, we want to model the entire probability distribution, and the trees, they detect steps and abrupt changes, they capture non-linear and non-additive effects and interactions quite well, and the forest, well, they stabilize and regularize the model, and they can model smooth effects as well. So how can we actually learn such a distributional tree and later on distributional forest? Well, as a starting point, we have the entire data set, so without any covariance. We fit a global distributional model to that by maximum likelihood for, well, any distribution we like, and we get that distributional model D, and here for illustration we look at the normal distribution. Well, a single global model is usually not sufficient for reasonably representing all the observations, of course, so we want to further split up that data, so for each subgroup a more homogeneous distributional model can be fitted. But the question here is, how can we actually do that? And we do that by evaluating the goodness of the fit for each parameter and each observation. We then pick the covariate X with the strongest influence on the goodness of fit as a split variable, and by accounting here both for changes within the location and the scale parameter, we actually have a full probabilistic model. And so we have here now the covariate X with the strongest influence, and then we look for the split point P in the second step, which leads to the highest improvement. And now, well, we have divided the data here, and now we just repeat the steps 1 to 4 recursively in the subgroups until some stopping criterion is met. So in the figure here on the right, we have 2 distributional models here, maybe with one smaller and one higher variance in the normal distribution. So the nice thing about the concept here is that I only ever have to fit the model on the response variable without any covariates, and that's because the covariates, they enter just as split variables in case they are associated with an improvement in the goodness of fit. And once again, for the goodness of fit, we consider all the distribution parameters, so we have a true probabilistic model here. Well, for the forest, we just learn an ensemble of 3 trees, each on a different learning data obtained either through bootstrapping or subsampling the data. And as I said, that stabilizes and regularizes the model. Well, let's look at an application here, probabilistic precipitation forecasting. So we have observational data over 28 years for daily precipitation sums for the month July. We look at one observation station in Tyrol located near Innsbruck. As covariates, we have numerical ensemble weather predictions of precipitation itself, so a highly informative covariable of course, but also forecasts of temperature, air pressure, and so on. And because we have here ensemble weather predictions, we have different realizations of the forecast, and we can build minima, maxima, mean, and standard deviations of these. In the end, we have 80 different covariates which go into our different models. And as a distributional assumption, we use here the power transformed Gaussian distribution censored at 0. So that's accounting that there cannot be any negative precipitation sums. So we have a point mass at 0. Let's look at the predictive performance. So from left to right, we have first here the distributional forest. Then we have in GAMLSS where we pre-specified the input variables. And then we have a boosted version of the GAMLSS. And we compare all these 3 to the heteroscedastic linear model called EMOS, which is kind of a standard model in the community of post-processing numerical weather forecasts. Well, we look here at CRPS skill scores, so positive values indicate an improvement in percent, and we have here 6% improvements over the reference model, the EMOS model. And the distributional forest is also competing against the GAMLSS versions of the models here. So in the paper, in the publication, we did the same for several stations within Tyrol, and this picture never really changes. Slight differences, of course, in the improvements. So whenever looking at a distributional model, one point is the predictive performance, of course, which we have seen on the previous slide. But the other point is if the predicted distribution actually matches the observed distribution. So in other words, do I actually predict the same distribution as observed? Well, to do that, there are various possibilities suggested in different parts of the literature. So we have the randomized quantile residuals plot, we have the probability integral transform histogram or PIT histogram, the rutogram, the reliability diagram for pre-specified thresholds, and the worm plot. In R, there are different bits and various packages available, but to our knowledge, there's no unifying and flexible infrastructure so far. So our newly developed package top models tries to fill that gap, and it's already working for several model classes, and more will come. So how can we use these packages? They are not on CRAN yet, so we have to set the repository to RForge. We install these packages, we load these packages, we load some illustration data available in the package dist-tree, and then we fit a random forest model. And here for performance issues, we used a pre-specified censored normal family, but we could also use any GAMLSS family object here. So let's look at some plots. First of all, the QQ plot. So the quantiles of the standard normal distribution are plotted against so-called quantile residuals, which can be obtained from probabilistic models. And as in the normal QQ plot, we have a rather good fit here if all the points are on the straight line. Here we have small deviations at both ends of the QQ plot, and we have an increased uncertainty here in the lower tail due to the censoring. Then the pit histogram, so this shows simply the value that the predictive CDF attains at the observations. So for a well-calibrated forecast, we should get a rather flat pit histogram, which is here more or less the case. Then the rutogram, where we evaluate if the observed frequencies match the expected frequencies. So here we have a so-called hanging rutogram, where the observed frequencies are hanging from the expected frequencies, the red line here. And we see we have a more or less perfect fit for zero precipitation due to our censoring. We have here a slight underfitting for low precipitation sums, but then a rather good fit here. And then the reliability diagram. Here we partition the predicted probabilities for an event. So here precipitation yes or no into a certain number of subsets. Then we calculate the averaged forecast probabilities and the observed relative frequencies for each subset against each other. And here we see again, when we are on the straight line, we are well calibrated or reliable, which is more or less the case here. A slight S shape here, indicating a slight underconfident model here. And then the warm plot, well, it's a so-called detrended QQ plot, again indicating a reasonably model fit here. Now, just for illustration, we look at a linear Gaussian model. It's of course not a good model fit. It's homoscedastic. It's not accounting for excess zeros and has an incorrect assumption of the underlying response distribution. So looking at the rutogram, now we have that typical wave-like pattern here. So we have here a clear overfitting for precipitation sums between 1 and 5. We are not accounting for the excess zeros here, so clearly underfitting the zero precipitation. Now we want to use custom breaks in our rutogram, and we see by these custom breaks now that we have a significant probability mass in the expected frequencies here due to no censoring. And now maybe for illustration we want to combine that plot with the random forest in one graphic, and we get the nice figure here by 2 lines of code. Now let's look at the pit histogram. Here we want to customize the plot as well. We use the style lines, which is better for comparison. We add to that forest model we already know, the linear model. We see that the central tendencies are now biased, and we get the figure here. And the QQ plot, first with the forest, then the linear model, and again we see that we have a right-screwed residuals here. And here we could also add any other model type basically, and different models either in one figure or several panels. So the software, well, this tree, it's available on RForge. It fuses the tree-based model concept with distributional modeling, and the main function we saw today was the distforest function. Then the top model software, well, top models, it's a unifying toolbox for probabilistic forecast and graphical model assessment. Here's already a nice packaged down web page available, and the main functions we saw today was the different plots. So various plots available, all can be rendered both in base R and ggplot2. They're highly customizable, and already different model classes are working, and more will come. So the list of references here, I want to especially emphasize the first one by my colleague Lisa Schlosser, which introduces the concept of distributional regression trees in forest and shows the same application we saw today. So here I want to conclude and thank you all for keeping to the end, and in case you have any further questions, don't hesitate to contact me per mail or Twitter.
Thank you, Moritz. Yeah, really great presentation. So there are some questions. So Pedro asks, I'm going to read out the question. Can this package take advantage of distributed computing on several nodes?
You mean like parallelized package?
I think so.
No, it's not parallelized at the moment. And at the moment, we really put the focus here on the plots. And of course, we don't need any parallelization for the plotting. Now, the next step is to increase the package that it actually supports more model classes as well. So at the moment, that's the limiting factor here, but we will work on that in the future now.
So there's another question by Alexander. They say, did you compare the prediction accuracy of the method as compared to non-parametric quantile random forests?
No, in the application, we really did that comparison of that random forest model here, the distributional random forest, to some versions of the gamma-S version, so semi-parametric models here. Yeah.
Okay, and Achim says to expand Moritz's comment. So Achim is also in the room. So he says the distry and underlying particle packages can make use of parallel computing, but top models not at this point. And then okay. So, and then Rachel says, very interesting and clear presentation. Thank you. Maybe I missed it. If so, I'm sorry. But did you test / compare the performance of the model in external data? I mean, external data is do you mean like real data sets, or Rachel, could you type, or do you want to unmute and say?
But the data we used here, it's we have to focus first on the distry. So here we of course looked at different data, and the application is real data. So it's comparing, as I said, precipitation forecasts to observations. And the top models package, here we also used real data, but also looked at simulated data. And here we are preparing at the moment a paper that actually analyzes the differences in the plots, that it's easier for the user to see in which different model assessment plot you can actually see the different pros and cons of your model. Yeah.
Right. So Rachel has just explained it. It's just a different. So by external data, what she means is just different from the one used to build the model. I mean, so this is, you're talking about test data.
Okay, yeah, the top models can actually work with the new data. So just as we know from LM, for example, we can also do all the different plots by using new data as well. Yeah, so in sample and out of sample performance measures.
Yeah, so Achim had said that if this was a question, both plots and numeric scores can be communicated in sample and out of sample, right? Yes, so I think those questions are answered. So we've got our next speaker, and this is, okay, so let me get these questions out of the way. Yes, okay, so our next speaker is François Rousset from the Institute of Evolutionary Science of Montpellier, at the University of Montpellier, and his research interests include evolutionary genetics, behavioral ecology, and host parasite interactions, and the theoretical and statistical issues raised by these topics. And today he's going to talk about spaMM and our package. Take it away.
Okay, thank you. Do you hear me?
Yeah, it's all good.
Yes, okay. So today I will describe features of the package spaMM and a standard R package to fit generalized, linear, and mixed models, allowing for complex covariance structures. So spaMM was first developed to fit spatial mixed models, hence its name, but it is now a much more polyvalent package, which can fit a wide range of models with features as shown here. And in the next slide, I will illustrate some of these features. It is also designed to be simple to use with a consistent syntax across models from linear models to mixed models. And it is designed to be robust and fast. Robust meaning in particular that it has high convergence rates for even for small data sets, but it can at the same time fit large data sets efficiently. From a methodological point of view, SPAM is based on Laplace approximation for the likelihood. So either for maximum likelihood or restricted maximum likelihood. And it uses distinct efficient matrix computation depending on the sparsity of the correlation matrix of the random effects, which can be sparse as in classical nested random effects, dense as in spatial geostatistical models, or have a sparse inverse. So the inverse of the correlation matrix is sparse as in spatial autoregressive models. And so thanks to these three different set of algorithms, SPAM can be efficient in all these cases. Here are a few examples of using SPAM to fit different models to show the syntax with a main function in SPAM, which is fitme. So this illustrates for linear model, generalized linear models up to generalized linear mixed models, the use of SPAM compared to standard function to fit the same models from other packages. And you can see that the syntax is the same in each case. In the next example, we consider more elaborate models. The first example is a classical model in quantitative genetics, where the correlation matrix of random effects is determined by the relatedness between individuals, the genetic relatedness between individuals, and this can be specified by the core matrix argument of the fitme function and by same named core matrix term in the model formula. Below you have a typical code to fit the same model by another widely used package. The next example shows how to fit a model with a model specifically for the residual variance of the variance of the residual error. And below you have the same model fitted by GLMM TMB, and you can see that the syntax is essentially identical. And finally, there is an example of a spatial model. So using the classical Matern correlation function for spatial autocorrelation of random effects. So it is specified by a Matern term in the model formula with the coordinates, the geographical coordinates used to specify the distance, the Euclidean distance between position in space. And SPAM can also use Earth distance, not only Euclidean distances. Below is how to fit the same model by GLM and TMB. So in all these cases, you can see how the fitme function can be used with a unified syntax for the different cases. We all want packages to be flexible and fast, but in fact, that has not been the first consideration in the development of SPAM. The first consideration was the first aim was to have proven performance in terms of controlled error rates. And by this, I mean, for example, that the distribution of the p-value of likelihood ratio test should be uniform when the null hypothesis is true, and we checked this systematically in the first step of development of SPAM, because the few alternative spatial procedures available at the time of first development were very poor in this respect. So I don't show such results, but there are extensive simulations in the first paper. Performance also meant low non-convergence rates. For example, for binary GLMMs, one often see that they fail to converge. And SPAM is very good from this point of view. But there are also known cases where, for example, the GLM function from stats fails to converge, and SPAM has a more robust function for fitting GLMs too, in that case. Once these objectives were attained, faster procedures were implemented without sacrificing such performance. So now SPAM is faster. It is still mostly R code, which makes it easy to extend. There are small bits of C++ code only for a few selected operations, mostly for the computer-intensive matrix operations. So SPAM is not always the fastest possible implementation of fitting procedures, but it exhibits a reasonable combination of speed, robustness, and evolvability of software. And I will illustrate speed in the next slides. So what follows are a few comparisons with GLMR for non-spatial models, with the INLA package for spatial models, and with GLMM TMB for both spatial and non-spatial models. Also, I show some results about speed. It should not be forgotten that there are also differences in the algorithms used, which may give different results in some cases. For example, for GLMM TMB versus SPAM, there are slight differences expected for response families with non-canonical link, such as gamma log response. But GLMM TMB and SPAM should give equivalent results for mixed models with response families with canonical link, such as binomial logit and Poisson log. I often see in simulation that GLMR tend to give different results from both GLMM TMB and SPAM when these two agree, and I have no explanation for that. To limit cherry picking of examples favorable to SPAM in the following comparison, they are based on examples used to showcase the speed of other packages in previous literature. And additional comparisons can be found in the gentle introduction that can be found at the following address. So in this first comparison, I have used the example, the simulation from figure the 1 and 2 of Brooks et al.'s paper about GLMM TMB. So these are for mixed models with negative binomial response families on long link. So this is just the fit me call to fit this model. So it has a simple structure, non-spatial. And the results show the increase in computation time with a number of observations in the data. And one can see that SPAM is faster than GLMM TMB itself, faster than LME4. On the right, where you have a similar comparison, but when increasing the number of levels of random effects, in the data. And again, SPAM is faster than GLM-TNB than LME4. For spatial models, we compare models with a classical Matern correlation function for the spatial random effect, which can be fitted by SPAM on GLM-TNB. But we will also consider the Markov random field approximation of constrained Matern models, which can be fitted both by SPAM and INLA. SPAM can indeed fit random effects with a Markov random field model defined by some INLA functions. I cannot go into the details of INLA functions, but there are some subtleties to keep in mind in using this function. We have parameters, cutoff parameters that controls the quality of the approximation of the Matern model, and an alpha parameter that corresponds to a fixed value of the smoothness parameter of the Matern model. So in the next comparison, I consider two values of the cutoff parameter, and I fix alpha to 2, which correspond to value 1 of the smoothness parameter of the Matern model. And these comparisons are based on an example provided to demonstrate INLA's efficiency. You have a link. The full data set has nearly 30,000 observations, and the comparisons are also made on random subset of the given number of observations. For all different models considered in the next comparison, again, one can use the Fitney function with a unified syntax. The Markov random field model is fitted in this way. So these are the geographical coordinates, and this is the object produced by the INLA function to describe the correlation model. Below you have the syntax to fit the Matern model, and the Matern model with a fixed parameter, fixed smoothness parameter, using the fixed argument of Fitney that can be used to fix basically all model parameters in a mixed model. So this slide shows first the comparison of speed of fitting the Matern model by SPAM and by GLM-TNB. SPAM in green is faster than GLM-TNB, but in fact, on this example, GLM-TNB had an over problem because these two fits terminated with an error. So you can see that SPAM is efficient, but the fitting time increased sharply with the number of spatial location in the data, which is a known feature of geostatistical models. So in the next slide, we compare the performance on the Markov random field model. So with the two cutoff values, you have SPAM in green and INLA computation time in blue. And you can see that SPAM is faster on the largest datasets. So in conclusion, SPAM is polyvalent, simple to use, robust and fast, as I have shown. It has other features that I have not illustrated. Any model parameter can be fixed. It has functions for parametric bootstrap, computing various prediction variances, marginal or conditional AIC, and so on. It is still in active development. The planned developments include adding a parametric correlation structure for multivariate response models that SPAM can also fit. And there are specific correlation structure used in quantitative genetics that will be added. One can also add or improve interfaces with other packages such as Boom Mixed or the Future package for parallel computations. And in the past, the development of SPAM has been driven by collaborations on various topics in ecology and evolutionary biology, and it is likely that future development of SPAM will also be driven by further collaborations. Thank you.
Thank you, François. There is a question. Hernan is asking, is there anything special, tricky one should be aware of when migrating from IMA to SPAM?
From INLA to SPAM?
No, not INLA. From IMER, IMA, or is it LMER? Okay, sorry, my mistake. It's LMER, yeah.
Well, as far as I know, LMER does not fit spatial models. So for non-spatial models, there are a few differences, but well, the difference I have shown fit me, but there are other fitting functions in SPAM that can be used, that were developed before fit me. And they have different default values of the method, either maximum likelihood or restricted maximum likelihood. So one must care about that. It's, I would say, the only feature one must care about, because for other ones, SPAM tend to give warnings of possible confusions.
Right, thank you. So I was also thinking, so you've compared SPAM with INLA and other packages. So with these were more spatial things, like, were they like hub? Is there, because when we are doing all the spatial statistics using different models and covariance structures, would there be, like, would there be things that you would say, sort of something to be aware of, or like wash this out, or is there something like that with SPAM?
Oh, well, I'm not sure what is the question. SPAM first implemented the Mattern correlation function, which is the most standard in geostatistics. There is also the Cauchy function. There are no other correlation function for geostatistical models in a continuous space. But so one can use the INLA models, and also one can specify any correlation model, in fact, as long as there is no parameters to fit in the model. I mean, one can specify arbitrary correlation matrices for the random effects. And also, one can fit several spatial random effects. I've seen someone fitting 6 Matterns random effects on a single data set. So in fact, the first time he did that, it was a bit tricky, and I have added a warning about how to handle the fixed effects in that case.
So since there are, so I have another. I had another question. That was like, have you compared SPAM with these with the spatial random forests that they have, because which is also used to build spatiotemporal data? Oh
yeah, well, yes and no. I am working with Alexandre Courtiol, who is a co-author of this talk, and he has done extensive comparison in the last months as part of a collaboration between using linear mixed models to fit some to make predictions, in fact, about some data sets I cannot detail. And comparing random forest methods for that. And so it's still work in progress, but the results were very similar, in fact, by both methods.
Yeah, thank you, François. Let's thank François. And so we don't. The next talk was withdrawn, and we're going to start at 10:15 because there might be people coming in for the talk by Gherardo. We are starting at 10:15 because that's the time that we address. Thank you so much, François, for coming. And then, if people have any, we still have some minutes until 10:15 because we were supposed to start then. And so if people would like to share what your thoughts are on how you're enjoying it or how you're not enjoying, if that's the case, the online experience of conferences. Well, you're welcome to put your mic and share, or just, give a shout in the chat, or whatever you'd like to do. Or if you've got other questions for François or Moritz, that's fine as well. So, yeah. So while we're waiting this time, maybe we can talk to Moritz again and then ask, Moritz, you said that your package, it says, okay, hold on, I just...
Let me just take the time here and thank once again all the organizers of that great user. And I know a lot of people have put a lot of work into organizing that virtual conference. And I think it's just a great way to keep connected here during the pandemic. So thank you from all of us, I think.
Thanks, Moritz. So your package is at this point, it's on top models is on our Forge right now.
Right.
Yeah. Are you thinking of putting it to CRAN, or is that like, or can it not be because, sometimes?
No, we are definitely planning to put it on CRAN, but it's at the moment, well, we started with the package a couple of months ago. So basically just a few months before the submission for the USR was. And so now we have already worked quite a lot on the different graphical assessment methods. And now we want to put more the focus on the probability forecasts, like the infrastructure supporting different model classes. And once that's all wrapped up, then we definitely will put it on CRAN. Yeah. You turn off your microphone.
Yeah, so you're going to put it on CRAN. François, your package is already on CRAN, isn't it? The SPAM package.
Oh, yes, it is. It has been on CRAN since at least, I think, December 2013, I think.
Yeah. So, so what is, maybe like, maybe I'm just asking really not great questions here, but I want to know, so INLA is not on CRAN, our INLA is not on CRAN because it cannot be for some reason. But you don't have that issue, even though you're doing like very similar kind of things.
Yes.
Can you?
Yes.
Yeah.
So in fact, one as so INLA is not on CRAN. To feed the models as I have shown with SPAM, you need to use two functions from INLA to generate the the correlation model. So you still have to install in there to fit using SPAM.
So with all the covariance structures that are there in the spatiotemporal domain, I've seen people use the Mattern covariance because it's kind of nicer in a way. What is your view or experience on these different covariance structures? Is there do you prefer one or?
For spatial models, because spatiotemporal, I have no practice of it really. But for spatial models, I have played with a few other correlation functions in the past, and I was never satisfied with the results. Really, the Mattern function is really very useful. Many people have discussed that before, but even when fitting data generated by simulation with another completely different correlation model, one following from population genetic processes, for example, I find that the Mattern correlation function can give very good results. So I tried also the Cauchy because there were extreme cases where the fits were not good for me, and so I tried something else than the Mattern. I tried the Cauchy. I implemented it in SPAM, but it didn't give notable improvements.
Yeah, thank you. I also wanted to ask Moritz, how it was with the whole. Do you want to comment on the when you're submitting? Maybe the people who are in the room are thinking of submitting CRAN packages or anything like that. So your experience both from François and Moritz, because we've got this extra time, why not talk about how we're going to do a package and what's the easiest way, to get a package done and, put it up there. What are the best practices, this kind of stuff.
Well, I can just say a few sentences because I haven't put any package on CRAN here so far. I have still 2 or actually 3 development packages I'm working on. So the DIS3 package, then we have also a circ3 package, and now the top models package. And for all of them, we do or we want to do testing. So top model is using tiny tests at the moment, and we have like a code coverage of 80 to 90%. So I think that's important step before you put it on CRAN. But then the final steps, how to do that, I want to maybe hand over to François because I haven't put anything there yet.
Well, on my side, I should say when I started to write SPAM, I was not familiar with R programming. So I surely did a lot of errors in the beginning. Now, so I don't systematically assess the coverage of the code using tools for that. So I have done it from time to time. I would say my first principle in writing code is that it should be easy to debug. So that's one thing. The second thing is that I tend to limit the number of dependencies. For example, SPAM can produce some graphics, and it uses only the base graphics functions, not ggplot or the like. And you have seen I have used the ggplot in the slides, but I would not use it in the package For example, because the syntax tends to change and so on. And I don't want to have to run after the changes over packages.
There are actually two questions now, which I didn't like. So Ashish is asking, I'm working on geographic weighted regression in survey sampling. Can you name some packages for it?
No.
Okay, Ashish, I think we'll have to see. And then Rachel says, spaM is a kind of an interesting and brave name for a package. Maybe do you want to go like, what made you come up with the name?
I like to make jokes with the name of software. So I have a population genetics software, which is called Migraine. And I developed an R package for simulation-based inference that is in some way a solution to the migraine. It is called Infusion for inference using a simulation.
So you like to play with words and then come up with
Yes.
a kind of a word.
Yes, but they should be easy to remember and easy to search on internet.
Thanks, François. And if there are any questions.
Sorry, the name top models actually came from, the show Top Models, because here we compare different models with each others. We have also like a function procast for probabilistic forecasting. So we basically cast the different models and then we compare them. So that's the name of Top Models. And when you go to our webpage, then you also see that we have a similar logo for that as the US show.
Yeah, thanks, Moritz. So when at one point in the package development, life cycle, like, you're writing code, you're testing, at one point, at which point do you pick your name and kind of think, okay, this is the name I'm going to, test whether it's check whether it's available. At which point does that happen?
Well, for that package, it actually was the decision of my former PhD supervisor, Achim Zeileis. And I think he had that idea already years ago. And when we started to work on that package together, the name was already given. And he said, like, okay, we have that Top Models package. And yeah.
On my side, I try to pick the name early because once you start writing the code, if you change the name, it poses problems.
Yes, thank you. So do we have other questions that you want to ask? So, yeah. So we have Gherardo's talk is, we've still got 6 more minutes, right? So because we need to start on time, because people might be coming just for this talk, and if we start before, they're going to miss out, and we don't want to do that. So that is why so if people have questions, or you want to talk, ask things about any let's ask François, because he's got the packages. What would your advice be to people who are making our packages, and what would be your advice?
So Alexandre is sending a message. I don't know if it's an answer. Well, as I said, really write the code so that it's easy to debug. That's really the first advice. second advice is do what I have not done. So have a assessment of coverage of the code in tests. I write a lot of tests, but I cannot measure everyday coverage. But I don't remember the details, but I have problems with measuring coverage with some of my functions. I don't remember why. What other advice? So yes, limit the dependencies, as I said.
Yeah, thanks, François. So, Moritz, I'm not going to put that on you, because I don't want to. I'm asking these questions so that we have some conversation points which hopefully are useful to the people who are in the webinar. And so, also, you said there was the book on Gentle Introduction to SPAN.
It's not a book. It's just a file.
Okay, a vignette, kind of it. Right. Haha. Yeah, because I was wondering, because sometimes people write the book down books as well about lots of their software, and when a software is decent, of a decent size.
Yes, I have some projects about some book length document, but and I have a lot of technical notes, but they are not necessarily very easy to read.
Maybe adding here to the insights or the lessons learned from developing your package, I think it's always good to start easy, to get an easy function and just few functions within your package, and then test maybe with tests, but also if you just get any failures or not, when you compile the package and you do the checks, which is provided for Sira, and then slightly adding to these functions, and not just writing a whole bunch of code and then just put all in a package at once, because that will fail at several places. Yeah. Yeah, and because we talked of the top model's name, I'm just putting the link in the chat. So there you see that nice logo, which was designed by Achim Zeileis and mainly Reto Stauffer and me. Yeah, just for sake of completeness. Thank you.
And I will present the R package, stage trees for structural learning of stratified stage trees. So what are stage event trees? Stage event trees are graphical models, probabilistic graphical models that are based on simple event trees. So what is an event tree? The event tree is a simple graphical representation as a complete symmetrical tree of a random vector, of the probability distribution of a random vector of categorical variables. In this case, on the left, we have an event tree for some of the variable in the Titanic data, in particular class, age, and survived in this order. Obviously, such an event tree is linked to a particular factorization of the joint probability distribution. We call such an event tree X compatible. So stage event trees are just a labeling of the nodes of an event trees. Indicate this labeling with colors. So we just color the nodes in the tree with the meaning that if two nodes at the same depth are of the same color, then the associated conditional probabilities are equal. So for example, in the last stratum of the tree, the one that corresponds to a variable survived, we have the two top nodes that are colored with the same color yellow. In this case, this means that the probability of survived given crew and adult is the same as the probability of surviving given that an individual belongs to the third class and is an adult. So then starting from stage event trees, we can also build another graphical representation, which is called chain event graph. And I'm saying this, I will not enter in detail, but just because a lot of times in the reference you will see the name chain event graph. So just to be clear that from a statistical point of view, they are exactly the same model, just a different graphical representation. So why the stage trees package? Today there is a rich literature on stage event trees, but there was just one R package implementing this class of model that was called the CHG package that was implementing stage trees and chain event graph. It is available on CRAN still, but is not actively maintained and was last updated in 2017. Moreover, it contains only one single algorithm to learn the stage structure, that is the coloring of the tree. So we started implementing the package at the end of 2018, and together with Manuele Leonelli, that is now at the EA Business School in Madrid, and Eva Riccomagno and Federico Carli from the University of Genova, we discussed this during the first UK workshop on probabilistic reasoning using chain event graph that was held at the beginning of 2019, and we decided that an implementation of stage event trees was essential to foster research in the field. I will present now some of the features of the stage trees package. For a detailed explanation, you can refer to the prepin. So at the core of the stage trees package, there is the class that represents the stage event tree model that is called the CFT class. That is basically a compact representation of the tree. This is, since the tree is complete and symmetrical, it's enough to describe the order of the variables and the levels each variable can attain. And then we have to describe the stages, that is the coloring of the nodes. And this is also done in a compact way, just with vector describing the labeling in every stratum of the tree. Moreover, of course, when the model is fitted to data, it also has to contain probabilities, conditional probabilities associated to each coloring of the nodes. So in the package, we have a different way to initialize such an object. There is a standard construct that is called CFT as a class, but this can be used especially for programming purpose and for to develop new methods. But from a user perspective, it's much easier to use the wrapper full or in depth, that they can directly build fitted stage event trees and isolate unobserved situation in special stages. So the full function, as the model suggests, build the saturated model where all the nodes are in different stages, and the in-depth function builds the full independent model where all the nodes at the same depth are in the same stage. So once we build like a standard stage event trees, like a stage event trees that are full or independent, or some other stage event tree that we can manually specify, we would like to learn the stage structure of the tree. And this is like the main contribution of this package, because we implemented a classes of methods that can learn the stage structure. To show this, I'm going to introduce first some simulated data on COVID patients. This data is simulated from actually a full stage event trees that is manually specified, using conditional probabilities that are available from this publication in 2021 from Lefranc et al. That was published in the Lancet Regional Health Europe, that describe ICU admission probability and survival rates for SARS-CoV-2 patients in France, conditional on age and sex. So the code is available in the R Markdown, but it's not shown here for space constraint. So we have data with variable sex, age, ICU, and death. So the first class of methods that we are going to see, they're what we call score methods, because they, similar to this called score plus search method to learn a DAG or Bayesian network, they work by searching the space of stage event trees and optimizing a given score, maximizing a given score. So each one of these methods can start from whatever stage event trees model, but here for simplicity, we start from the full, the saturated model, so the more complex model. The first two methods, the backward hill climbing and the fast backward hill climbing, they are backward methods. So they try to simplify the model by aggregating stages together, while the hill climbing method can both aggregate and split stages. So moves in both directions towards more complex or towards more simple models. And these are hill climbing methods, so they are heuristic that try to optimize the score that can be provided by the user, and by default is the negative BIC score. On the other side, we have some clustering method that instead of optimizing a given score, like the BIC criterion, they operate directly on the conditional probabilities that are estimated for each variable given the past of the tree, and they try to cluster these probabilities. So we have a backward joining algorithm that just join similar probabilities until a given threshold. We have a hierarchical cluster method and a k-means cluster method that are just wrapper of the corresponding clustering function available in the stats package. We have to say that most of the functions play nicely with the pipe operator that was introduced in R recently. So, for example, we can combine different learning algorithm over different variables using the scope argument of the learning function. And as in the second example, for example, we can use the standard naming function to rename the stages of the tree. So another feature that we just recently introduced in the package in the last version is the possibility to search of the optimal order of the variable, because until now we have seen algorithm that operates with a given order of the variable. So we initialize for example, a full stage event trees, and then we can learn just the coloring of the nodes. But instead, sometimes it's useful to being able to search all the possible ordering of the variable that give rise to the best scoring, for example, model. And we implemented the dynamic programming approach that was introduced by Seelander and Leog in 2013 that actually find the best ordering among all possible ones. And then we also implemented a simple greedy heuristic. The last way, let's say, to build stage event trees is to convert them from Bayesian network or DAG model. In particular, we have a conversion method that works from the BN and BN fit class in the BN learn package. And moreover, we implemented also the other way around, the conversion from a stage event tree into a Bayesian network. So finally, we also developed, apart from learning algorithm and conversion algorithm, we developed a battery of function and utilities that are able to plot, to compare, and to do some inference on the learned model. We're going to see them now. So plots, we introduced like a very simple plots of a stage event trees where it's possible to specify the palettes for the nodes, for the stages in different ways. Here, for example, I'm using a function with the Viridis palette. And similar, we have a function, we have a bar plot method It's useful sometimes to visually depict the difference in conditional probabilities. Here, for example, we can see that stages that are colored in yellow for the death variable, they are stages that correspond to context where the probability of death is higher. For example, we have especially male patients and older patients, both male and female. So we also introduced some comparing function. So given two different models over the same variables and with the same order, we can compare their stages to see if they're different or not, because sometimes maybe two models, they can have different labeling, different names of the stages, but then they represent the same model. So we introduce like a comparing function. We have the Hamming stages function that computes the number of nodes that must be changed in order to obtain one model from the other one. So it kind of like a distance between models. And then we have other function like inclusion stages that checks if one model is included in the other one. Recently, in the new version of the package, in version 2.20, we also introduced a new comparing function that we call it CID, for context-specific interventional discrepancy, that can actually operate between models that have different variable ordering and computes a kind of causal meaningful distance between the two models. So what about inference? We can compute probabilities with the prob function. We can compute also conditional probability with the same function, confidence interval for the estimated conditional probabilities with using different methods. And we can use the model to classify as a classifier with the predict function. Moreover, we can also compute the BIC score, for example, the log likelihood. And we have finally a likelihood ratio test function that is available in the last version of the package that computes likelihood ratio tests between nested models. So this is all, and I hope you will find interesting the stage trees package. In this case, you can contact us through GitHub or through the email. The package is available through CRAN, and the last developing version is available in GitHub. And it's under the MIT license. And for more detailed description of the method, you can refer to the preprint that is available on arXiv. Thanks again.
Thank you, Gherardo. So Gherardo Varando he's from the University of Valencia, and his research interests are in probabilistic and Gaussian graphical models for dynamical systems, staged event trees, chain event graphs, and asymmetric graph models. So he was talking about the package, and I was meant to have done it earlier. Apologies for doing it later. So so just checking the questions. Well, I've got a question. The Hamming distance that you're comparing one model and how many should change to go to the next model, that kind of things. When would you use that in practice?
Yeah. Can you hear me, right? Okay. Yeah. I mean, the idea is that sometimes when you want to do some studies, that you want to check if your model is actually learning the real model. If you simulate data from a stage event trees, then you need some function that you want to quantify the distance between two models, like the structural distance, let's say. This is something similar that in Bayesian network or in DAG, use something called like the structural Hamming distance. So this was like an equivalent distance that we think it was useful to have. Then actually, we didn't use it so much, but yes, it could be used to compare to model. Like if someone wants to have like a simulation. I mean, we're thinking now to do some like simulation studies to see when this learning algorithm converge to the true model when you simulate from stage event trees, and this could be one way to do it.
Yeah, sorry, that was what I was thinking, like in the sense I was thinking, like, whether you can use it in the convergence process if you're using like a Markov chain, like, or something like that. Would others have questions? So let's see. So stage trees has gone through lots of versions by this point, isn't it? Like you've been like, because it's 2 point something like, so this is, are you like, what are the recent features that you've put in?
Sorry, I mean, why the package has gone through a lot of versions?
No, I mean it's good for it to go through functions. What I mean is, like, of course, people are constantly adding. You start with something and you add more functionality or update functionality, or so I was just more interested in what would be new functionality that would be there, as opposed to like how it has changed.
Yeah, I mean probably we made some mistake because we I mean, when I started developing this package, I had some experience developing packages, but not like bigger packages where you build everything like a class for a new model and then methods and stuff. So maybe I made some naming, strong naming choices at the beginning. So we had like after the first version, we had some iteration with 0 point something. Then we moved to 1 because we had some big changes. And then, I mean, it's because also the preprint is under submission. And then we had some major suggestion that was the very right suggestion from the reviewers that the naming of the function was wrong. And so we made big changes, and we also used this opportunity then to change a lot of things in the package, so we moved to version 2. But now I think, I mean, it's a bit more stable. And then last iteration, there just have been like some. We are trying to use this same versioning, so we're just using some patches and some minor version when we introduce new functions. And now lately, the function that we introduced in the last iteration are like. Because we did some research and we have some preprint that should come out at some point on something related on causality that I think it should be an archive already. So we try to use this model to learn causal relationship, basically. Because usually in the causal literature, you use a lot of like DAGs or Bayesian networks, I mean, to learn causal. But this kind of model, they cannot represent what we call non-symmetrical conditional independent statement, like maybe you have some variables that are conditional independence on another one only in some context. I mean, only when some other variables that we call context, they assume some values, in particular values. I mean, in the Titanic data set, you can have, now I'm just making an example, that survival probability can be independent of age if you are in the first class, for example. Which is probably not the case, but I'm just making an example now. So this kind of context-specific conditional independent statements are not representable in the graphical, just in the graphical representation of DAGs over Bayesian network. They are representable just by the graph in stage trees model, because you just color with something the nodes. And so they're more expressive, let's say, in a way. And the idea is that maybe if there are such statements, are context-specific statement in the model, then we can use this and leverage this information to learn the causal order of the variable, let's say. And this, we just started like this line of research. So in the last iteration of the package, we just added this context, this causal meaningful distance, let's say, that is a bit inspired by what is called the structural intervention distance in the DAG case, that is similar things. You basically try to count the number of wrongly inferred intervention by a second model with respect to the true one, say. So we try to do the similar thing. And this is function. And then we have this order searching function that they optimize over different orders of the variables and try to search the best model. And but this was not introduced by us, but we just implemented this dynamic programming approach in the package.
Yeah, thanks, Gherardo. So the causal statistics and the causal part of research is kind of really taking off, and that's kind of a really hot topic in many areas. And so you're also getting into that with the stage trees and stuff, which is like really, really great. Yeah. So if there are there are no more questions at this point. Yes, thank you so much to all our speakers, to Moritz, François, and Gherardo. Thank you for for the talks, and thanks for everyone for coming. And thanks, Nick, for doing all the technical support at the back. And hope you enjoy your day.
Thank you. Thanks, Giovanni.
Thank you.
Thank you. Bye.
True.
Bye-bye.